Hi guys, this is the fourth video. So video 1.4, unit 1, video 4, you should be watching it Tuesday, 9/13. A limit is the final, utmost, or furthest boundary. And when we're talking about limits in calculus, we're talking about limits of functions or their graphs. The limit of a function, this is new, the limit of a function exists if and only if both the left hand and right hand limits exist and are equal. So today we really haven't talked about limits yet. We've talked about, well, types of limits, left hand and right hand limits, but today we're just going to talk about the limit period of a function. And that limit is going to exist if and only if the left and right hand limits exist and are equal. So on the first page here of these notes, guys, we're going to be looking at this graph here, okay? Let's notice first some characteristics of the graph. It has what's called a discontinuity at this point here at x equals -8. This is called I think this is called a removable discontinuity because the function has a hole here, but it is still defined at x equals -8. It's just defined up here instead of at where that hole is. All right, here's another discontinuity of the function. Notice on the left side or the right side of it, there's an asymptote. And then there's another discontinuity here at x equals 6. That's called a jump discontinuity because it's like the function is going like this and then it stops and jumps to another value. Okay, so the left-hand limit at x equals -8. All right, so make sure that you're paying very close attention to my notation here, guys. When I'm doing the left hand and right hand limits before I do the just limit period of the function, I'm going to use arrow diagram notation in these two spots, and then I'll use very formal notation here. Okay, that when students are using calculus, the notation I'm going to use for part C sometimes gives them trouble. All right, so as x approaches -8 from the left, that's going to be the left-hand limit, and then I'm also going to do as x approaches -8 from the right. And I'm going to ask myself what y is approaching. So y approaches what? All right, I'll do parts A and B really at the same time. So I'm just going to look at the graph, guys. I'm not going to do a table of values like I've asked you to estimate before. I'm just going to, look at the graph. So x is approaching -8 from the left. All right, so as my x's get closer and closer to -8 from the left, like -8.1, -8.01, -8.001, those values for x correspond to this part of the graph, whose y values are over here. And as x is approaching -8 from the left, the y values are getting closer and closer to -6. All right, so that was for the left. Now I'll do for the right. So x is approaching -8 from the right. So -7.9, -7.99, keep adding nines. We correspond to this part of the graph, which is again corresponding to these y values here, which are approaching -6. Now for part C, I want to know the limit at -8. And the limit, guys, the limit of a function exists if and only if both left-hand and right-hand limits exist and are equal. Well, guys, they both exist and they are equal. So that means in the end, okay, now this notation is important, that the limit as x approaches -8 of this function, which I will call f of x, equals -6. All right? So the limit of a function is going to be the value of both left and right hand limits. All right, so up here, we're going to call this function f of x. Alrighty? So guys, this is new. The language I'm using is new. The notation might be a little bit new. Just stick with it and you'll pick it up. So the left hand limit at -2 and the right hand limit at -2. I'll start going a little bit faster. Alrighty, so as x approaches -2 from the left, as x approaches -2 from the right. I'm going to back up for a second. Notice something new today. I don't have a plus or a minus up here. that means that this is just the limit period. The number that I am approaching as I approach x equals -8 from the right and left at the same time. So if you don't see a plus or minus up here, it means you're thinking of plus of from the left and right, plus and minus at the same exact time. Okay. Alrighty. So as x approaches, so I got to think of what y is approaching. -2 from the left. Okay, -2 approaching from the left, so -2.1, -2.001, etc. I'm looking at this part of the graph whose y values are approaching 3. Okay, so as x approaches -2 from the left, y is approaching 3. As x is approaching -2 from the right, there's that asymptote that I pointed out at the beginning. So -1.9, -1.99, -1.999. This is an asymptote. Those y values are getting huge. They're going off the page. So y is approaching infinity. Now the limit at the end, guys, the limit of a function only exists if the left hand and right hand limits are agreeing. Here they are definitely not. So over here I'm going to say that the limit as x approaches -2 of this function, which I'm calling f of x, does not exist. If you want to put like an equal sign here, equals does not exist, that's not bad. It sounds a little bit unprofessional because you wouldn't say it equals nothing. It does not exist. So I'm not going to put an equal sign there. But if you're a little uncomfortable with this empty space, you can put an equal sign. That is fine. The limit as x approaches -2 of f of x does not exist. Okay, guys, we're going to do another one. If you're getting the hang of it, you can jump ahead of me. And then, like I always say, just make sure that you check and make sure we got the same thing in the end. X is approaching 6 from the left. X is approaching 6 from the right. I'm going to ask myself what y is approaching. Okay, back to the graph. 6 from the left. I'm looking at this part of the graph. The values are just right up above 2. Okay, so as x approaches 6 from the left, y is approaching 2. Now the right. As x's are approaching 6 from the right, I'm looking at this part of the graph whose y values are right above and approaching 5. Okay, so y is approaching 5. So since the left-hand limit and the right-hand limit, they both exist this time. Previously, the right-hand limit didn't even exist. But they both exist this time, but they are not agreeing. They're not the same. So again, we have a situation where the limit does not exist. So the limit as x approaches 6 of this function f of x, again, does not exist. One more, and then we got some on the back. We're making pretty good time. Alrighty, so x is approaching 10 from the left, x approaches 10 from the right. Okay, so I'm looking at my picture here. So approaching 10 from the left, I'm looking at this part of the graph there, whose y values are just right up above and approaching 0. Approaching 10 from the left, I'm looking at this part of the graph here, whose y values are right below and approaching 0. All right, so guys, it looks like we do have a limit here. See? Whoops. I don't know what I did. I was trying to make it less blurry and I did something. Okay, so sorry it's blurry now. Down here, y is approaching 0. And again, y is approaching 0. I don't know why it got so blurry, sorry. Okay, sorry. Okay, so we have both left and right hand limits. They exist and they are equal. So that means that the limit as x approaches 10, okay, so the limit as it approaches from the left and the right is 0. Okay, now we're going to move to the back. All right. Okay, so we're going to do 2 examples up here, and then we're going to finish off with the bottom, and then homework will not be that long, guys. Okay, so finding 2 more limits graphically. Guys, here we have 2 situations with asymptotes. Now, for the first one, as x approaches, so the question is, what is the limit of the function as x approaches 0? And the function we're working with here is y equals 1 over x. As x, so we have to look at the left and the right hand limits. As x approaches 0 from the left and as x approaches 0 from the right. Okay, now we know we have an asymptote, so the limit is not going to exist, but can we be more specific? Does it plain old not exist, or is it infinity or negative infinity? Okay, x is approaching 0 from the left. We have this asymptote, and the function's going way, way down. So y is approaching negative infinity. From the right, we've got this asymptote, and the graph is going way up, so y is approaching positive infinity. So the limit does not exist, because from the left and right, we do not have an agreement. So the limit as x approaches 0 of this function, which I'll just write in there, 1 over x, does not exist. All right? Ooh, and right before, I'm going to put that triangle of points there, which means therefore. So as x approaches 0 from the left, y approaches negative infinity. As x approaches 0 from the right, y approaches positive infinity. Therefore, the limit as x approaches 0 of 1 over x does not exist. Okay, now here, guys, we have a very similar situation, except from both the left and right, as we approach 0, the graph is going up to positive infinity. So we've got x approaching 0 from the left, x approaching 0 from the right, y, those y values are approaching, positive infinity, and these y values are approaching positive infinity. Therefore, the limit as x approaches 0 of this function here, which is 1 over x squared, I'm going to say equals infinity. It still doesn't exist, but we can be a little more specific because it is agreeing on the left and right. It has the same type of non-existence from the left and right, so I'm going to say equals positive infinity. Okay, guys, so we've got, we're up to 13 minutes. I will make this fast. Go ahead of me if you'd like. I will cut down the homework also. So we're going to find the following limits here using our calculator. Please show your table of values for the left and right hand limits. Okay, so I'm going to take my calculator and I'm going to graph. It's the same function every time. Okay, so I go to y equals, I'm going to graph my function. This is x squared minus 9, close parentheses, divided by x squared minus 10x plus 21, close parentheses. I want to make sure that my table is set to ask for the independent variable. And I can go to my table and I will plug in the values. So before I do that, let me set up my tables. I'm going to use tables for the left and right hand limits. Alrighty. So here for this first one, I'll do a table of values. I'm approaching 3 from the right, so I'm to the right of 3 and approaching it. So think of going this way on the number line. So numbers to the right of 3. 3.1, getting closer, 3.01, 3.001. All right, I'll get those y values in a moment. Then I've got to approach 3 from the left. Okay, so I'm approaching 3, going this way this time. So a number to the left of 3, but pretty close, 2.9. Get closer, 2.99. Even closer, 2.999. All right, now let me get my y values. Okay, so from the right, 3.1, enter, 3.01, 3.001. Okay, so I've got these y values, which I'll write down and then talk about what they mean. We've got negative 1.564, negative 1.506, negative 1.501. And it looks to me, guys, that as x is approaching 3 from the right, the y values are approaching negative 1.5. So negative 1.5, I'm circling that. That is the left-hand limit there. That's the answer to the limit at the top of that column. Okay, now from the left, 2.9, 2.99, 2.999. All right, I'm going to write those values in. 2.9, negative 1.439. 2.99, negative 1.494, negative 1.499. And as x approaches 3 from the left, the y's again are getting closer and closer to negative 1.5. That is the number we are getting closer and closer to, but never passing. So negative 1.5 again. So the left-hand limit and right-hand limits are agreeing. That means that in the end, the limit as x approaches 3 of this function here is negative 1.5. Okay, guys, this was about a 17-minute video. I'm going to cut down the homework a little bit. And so I'm telling you what your homework is. From the homework packet, the homework corresponding to video 1.4 on pages 10 and 11. So 10 and 11 in the homework packet. Everything up to 3. All right, so you can stop. So you don't have to do the rationalizing the denominator stuff. All right, so stop up at, so you'll do everything up to here. Okay, guys, I'll see you tomorrow.